Red Planet, the history of water, the possibilities of life.
You learn something and then you design the next mission based on what you learn.
Has allowed us to literally go back in time on Mars.
The first picture will cover an area of 176 miles.
Mariner 4 began transmitting back images.
The first photograph that a human being has ever seen from the surface of another planet.
On August 20th, 1975, the first Viking spaceship was launched.
You are seeing something that no other human has ever seen before.
Former seas and mountains.
Huge canyons.
That sense of wonderment and achievement and always working towards your goal.
We can do, and we will do.
And liftoff.
Touchdown confirmed.
Mars is unavoidably special.
We've landed and we've scooped.
We've roved, weve orbited.
Together, we did it, but the attitude was together we can do it.
The future is what you make out of it. You can make it real.
And here we are with Mars Perseverance, 51 years later, getting ready to do the first ever Mars return mission.
Eventually, we can bring those samples back to Earth and determine for the very first time, did life exist on Mars?
Good afternoon, everyone, and welcome to the NASA Kennedy Space Center for the Mars 2020 Mission Tech and Humans to Mars briefing. I'm Tammy Long of NASA Communications, and this afternoon we are going to unpack some truly spectacular technology on board the Mars Perseverance rover. We encourage you to follow the mission at NASA Persevere, and we would love to have your questions for the panel. Please use the hashtag #CountdownToMars. It is my distinct privilege and honor to introduce this amazing panel. We begin at NASA headquarters in Washington, D.C. with Jim Watson, the director of NASA's Mars Exploration Program. Live with us in studio is Dr. Jeffrey Sheehy, chief engineer of NASA's Space Technology Mission Directorate. Then we're blasting west and going to the Jet Propulsion Laboratory in Pasadena, California for Mimi Ong, the project manager of the Mars Ingenuity helicopter. Then we're launching back to the East Coast to Cambridge, Massachusetts, to Michael Hecht. He's the principal investigator for MOXIE and the associate director for the MIT Haystock Observatory. And then, of course, we're coming back south to the Johnson Space Center in Houston, Texas for Amy Ross, who's a planetary spacesuit engineer. I want that on my business card. And finishing off with Michelle Rucker. She leads a cross-agency team for architecture and operational concepts for the first human mission to Mars. Wow, what a panel. So let's get it kicked off with Jim at NASA headquarters, who's going to give us a quick Mars 2020 overview and tell us where it's leading us. Hello, Jim.
Thank you, Tammy. Boy, I just have to remark those videos that you teed up this whole event with. They never get old. I have a chart here that I brought along that sort of summarizes some of our more recent history. And what I wanted to do and address this afternoon with everybody is explain a little bit how we were able to accomplish so much. So if you look at the past 20 years, NASA has been following a very focused and strategic plan to explore Mars. And it's been guided by setting a strategy of what we call follow the water. And we did that because we know that water is key for life here on Earth. It's also key to how the climate behaves. It's also key to understanding how the surface of a planet forms. So starting back at the around 2000, actually the late 1990s, we started with a series of orbiters. And these orbiters we sent to Mars to do remote sensing, to capture imagery so we could create the maps of what the surface looks like, what the geology looks like, to characterize it, get a sense for the mineralogy that's on the surface, and start to form our understanding of how that planet may have formed and how that surface has evolved over the time. But we knew to do the real serious work, we had to get down to the surface. So we started in 1996, we sent a very small rover. You'd hardly recognize it today when you compared it with the Perseverance rover. It's a tiny little thing, a little bit bigger than a shoebox. And that we landed on Mars, and that's how we first learned how to survive on the surface of Mars and how to operate on the surface of Mars so that we could do work. We could do exploration work. We learned a lot from that, and so we established a new program that had the Spirit and Opportunity rovers. We sent those two together as a pair, and very, very successful program there. So Spirit and Opportunity together established that Mars truly was habitable, that it had abundant water on the surface in many forms, in the forms of large lakes, small lakes, flowing rivers, even hot springs. So with that knowledge in hand and the experience that we gained operating these Spirit and Opportunity rovers, we went and developed what has been our flagship to date, and that's the Curiosity rover. Almost a metric ton in weight and outfitted with a lot of very, very precise instrumentation, including a mass spectrometer to help tell us what the molecular structure was of the samples that we were able to probe. We've been exploring Mars since 2011. And from that success and from the data that's returned from that, we have commissioned the Perseverance rover on the Mars 2020 project. And we're going to launch that on Thursday. And that rover is following in the footsteps of that legacy of rovers. So we'd try something first, we'd learn from it, we'd evolve new technologies, apply them and feed forward into the next rover. We'd learn some more, feed them forward into the next rover, and Perseverance is no exception. Perseverance is loaded with new technology, new operational techniques that we're going to experiment so that we can explore Mars in even greater detail. And in fact, we're setting up the next great campaign at Mars, Mars Sample Return, in the sense that Perseverance is going to take samples and cache them, and they'll be retrieved by future missions and bring them home to be studied in laboratories here on Earth. So you might ask, well, Perseverance, looking at new technologies that will enable future exploration, what possibly do we have yet to learn? Well, we still have a lot. Okay, we still can't land exactly where we want to be. The error circle for Perseverance is on the order of 10 kilometers. When we send humans to Mars and when we pursue sample return, we need to land even closer to where we want to be than that. So we hope to improve that yet another order of magnitude. And so there's technologies that we're going to use in the Perseverance landing. We're going to experiment with how we can get even closer. We've improved our algorithms for how we deploy our parachutes, and we've added a new sensor that can view the terrain on the final descent, and from that we can determine if we're flying towards hazard and take corrective action. We also, when we explore Mars in the future, we want to be able to live off the land in some respects. We don't want to have to carry everything that we need. And so it's going to be very important for future explorers, both robotic and human, to be able to get some substance from the planet. So we have an experiment on board, a technology demonstration you'll hear about today called MOXIE, and it's going to extract oxygen from the atmosphere. We also have an instrument on Mars 2020 as a ground-penetrating radar, and we're going to start to probe the upper 10 meters or so of the surface of Mars, understand the soil structure and the rock structure, and start to do the necessary civil engineering where we'll have to know whether that soil can support the larger landers that humans will take in the future to go to Mars. We also need to forecast the weather better. Okay, if you recall, not too long ago, we lost the Opportunity rover, and we lost it because there was a planet-enveloping dust storm that obscured the sunlight and it can no longer charge its battery. When we have human explorers on Mars, we want to be able to forecast these before they happen so we can take precautions for the safety of the crew. And lastly, we need to be able to come home. So Mars Sample Return, the first round trip to another planet, that will be the first time using robotic systems that we land, get samples from another mission, get the treasure that we find in exploring, and launch them back into Mars orbit, and then ultimately bring them home to Earth. We want to run those trap lines, if you will, with robotic systems before we develop the larger and more expensive and more capable human systems. So you're going to hear about some of these technologies this afternoon. They're very exciting, and they all contribute to the future of exploration.
Thank you, Jim, for setting up our Mission 2020 for the overview. And now we would like to ask Jeff to talk about some of the new technologies that are being featured in the Mars 2020 mission.
Well, the agency understands that technology drives exploration. And in the Space Technology Mission Directorate, we're super excited to have some technologies on board the Mars 2020 mission and the Perseverance rover. Jim laid out the plan for this mission and highlighted some of these technologies that are being included on the mission and will go to the surface with the rover. This mission will contribute to enabling human exploration by giving us technology that can help us land more precisely in more hazardous locations. A lot of the interesting places you want to explore on Mars are also hazardous places to land your spacecraft, and so having precise landing technology is really important. It'll provide technologies that will allow us to live off the land, to utilize resources that we find on Mars to make commodities that we need to do exploration missions, and even, as Jim mentioned, to forecast the weather. We've worked with a variety of partners, Science Mission Directorate, Human Exploration and Operations Mission Directorate, several of the NASA field centers, even the Spanish National Research Council on these technologies. And there are 4 particular items that I'd like to highlight for you today. 2 of these will be utilized during the entry, descent, and landing phase of the mission, those 7 minutes of terror when the spacecraft first enters the atmosphere and then is descending all the way to the surface. And then the other 2 technologies will be utilized when we reach the surface during the surface operations of the rover. The first of the technologies I want to highlight is called MEDLEY 2. That stands for Mars Entry, Descent, and Landing Instrumentation. And it's the second round for this. We have an image that I'd like to show that shows the spacecraft. You can see there the heat shield on the bottom and the back, what they call the back shell on the top. And embedded in the heat shield and the back shell are a number of instruments. There's thermocouples, there's heat flux sensors, and there's pressure transducers. And they collect data at the various locations on the heat shield during the descent and the back shell, during the descent through the atmosphere on those last 7 minutes of flight. When we take measurements of this nature, we answer a lot of questions, and when we look at the data, we realize that we have new questions. And so MEDLEY 2 builds on the heritage of the 2012 landing of Curiosity, where we had similar types of instrumentation, not in all the same locations, on that flight, and we learned a lot, and we raised some new questions, and some of those questions we're going to answer on this flight. The way we use the data is to validate models that we use when we develop new spacecraft that we want to land on Mars. Jim showed the progression of rovers from small little rovers to things like Perseverance that's the size maybe of a small SUV. Well, for human exploration, we're going to have to land something the size of a 2-story condominium on Mars, something that weighs 20 tons or more, not just a ton. And so, I mean, it's amazing to be able to land a ton on Mars, but eventually we're going to have to land 20 tons on Mars. And so as we design the new landing systems and the new spacecraft that we have on Mars, it's important to be able to model that landing portion of the mission and make sure that we can land those systems safely. So the data we get from MEDLEY 2 will be able to provide that validation for entry, descent, and landing models. Another technology that I want to highlight is called terrain relative navigation. It allows us to pinpoint the landing zone on Mars, and this is a technology that will allow us to land more accurately in the locations we want and in more hazardous locations. You know, in Apollo 11, Neil Armstrong looked out the window and said, I don't really like where we're headed here. or something very close to that. And so he took over control from the automated guidance system of the lunar lander and guided it past the crater, guided it past some large boulders so that he could land safely at the Sea of Tranquility. Well, we don't have Neil Armstrong or any other astronaut on board the Perseverance landing, but we do have terrain relative navigation, and it provides us with two very important things. One is better knowledge of where is Perseverance over the surface of the landing zone, and then the ability to divert if we see that we're headed toward an unfavorable landing area, just like Neil Armstrong did on Apollo 11. It has a lander vision system that compares images, and actually we have an animation of this that we can show. It compares images of the landing site that are being taken as the spacecraft descends through the atmosphere with maps that have been prepared from orbital missions. And so it can get some information on where it is over the surface of Mars. Then that information is fed into a safe target selection system that calculates where the rover is going to touch down, and then compares images with different maps that have identified in the maps the safe landing zones and also especially bad landing zones. And so if it sees that Perseverance is headed toward a bad site, it can institute a divert. The landing system thrusters will fire and move the spacecraft toward a more safe landing site. This is the kind of technology that we'll need, as Jim mentioned, to land several assets in close proximity to each other in order to enable human exploration at some future date. So I've talked about two technologies that will be used during the entry, descent, and landing portion of the mission. During operations on the surface, there are two additional key technologies that I want to highlight. The first of these is called MEDA, M-E-D-A. It stands for Mars Environmental Dynamics Analyzer. It's a contribution from the Spanish National Research Council with funding from NASA, particularly the Space Technology Mission Directorate. It's a collection of sensors that are designed to detect the amount and the size of dust particles in the atmosphere on Mars, as well as make a bunch of weather measurements, kind of similar to what you might make with your weather system in the backyard. It'll measure the temperature, both the air temperature and the ground temperature. It'll measure the humidity. It'll measure the atmospheric pressure. It'll measure the solar radiation, and then it'll accumulate all that data, and we'll be able to determine how the environment, the weather environment, the environment that we find on Mars, affects the performance of systems on Perseverance. And then ultimately, when we land astronauts on Mars, and one of them turns to another and says, "Hey, what's the weather like today?" they'll be able to have a weather forecast of what the weather's like on Mars. The last technology, I didn't leave it for last because it's the least. I left it for last because Mike Hecht, the principal investigator, will be talking about it in just a little bit. And so I don't want to steal too much of his thunder, but I'll just mention it. Jim Watson mentioned it also. It's called MOXIE. The name of it kind of invokes a certain kind of attitude that I think is appropriate for this kind of ambitious mission. It's the first ever in situ resource utilization experiment on another planet. It's going to suck in the atmosphere of Mars and turn it into oxygen. I saved it for last because Mike will talk about it, and I'm sure he's eager to tell you about it, so I won't say any more about MOXIE. But I'll just close by saying that Space Technology Mission Directorate is excited to be part of this fabulous mission. I want to thank Jim and his colleagues at Science Mission Directorate for letting our technologies ride along with him, and thank you all for letting me describe them to you.
Thank you, Jim. For a non-technical mere mortal like myself, it is absolutely mind-blowing, the technology we're sending on the Mars Perseverance rover. And on that note, we're going to the Jet Propulsion Laboratory to speak with Mimi, who's going to take us to an introduction for the Mars Ingenuity helicopter, another extraordinary experiment. Mimi?
Thank you, Tammy. Hi, so this is full-scale model of the Mars helicopter Ingenuity. So the Mars helicopter technology demonstration on Mars 2020 will attempt the very first rotorcraft flight at Mars. In fact, we as human beings have never flown a rotorcraft outside of our own Earth's atmosphere, so this will actually be very much a Wright brothers moment, except on another planet. Well, flying a rotorcraft at Mars is very difficult. First and foremost, the atmosphere there is very thin, about 1% compared to the Earth's atmospheric density here. And so to build a vehicle that can fly at Mars, it has to be very light and be able to spin very fast. So going on to the model here of our solution, okay, there is a solar panel that will garner solar energy from the sun. There is an antenna for wireless communication. It has a rotor system. Ingenuity has a 1.2 meter diameter rotor system, 2 pairs of counter-rotating blades. They'll spin about 2,400 revolutions per minute. And under here is a fuselage that contains a battery that will store the energy gathered by the solar cells, and it's surrounded by custom lightweight circuit boards that will perform onboard autonomous flight and landing, onboard management of the thermal, the temperature based on the temperature sensors. It will manage the onboard energy. It will perform the telecommunication. And the fuselage is also equipped with onboard sensors, so cameras, accelerometer, gyros, inclinometer, and an altimeter for the vehicle to use with an onboard estimation of the state for the onboard autonomous flight. And then the vehicle has the landing gear. The entire vehicle that you see here weighs in just under 1.8 kilogram. That's just about 4 pounds. And that's been the very beginning fundamental challenge of building a rotorcraft that can fly at Mars. So there is a significant team behind making this happen. I'm very happy to be here on behalf of the team. And this 1.8 kilogram challenge is tackled by this large team from JPL, multiple centers across NASA and critical industrial partners. And we worked very tightly together, rolled up our sleeves. We had to set aside our traditional technical boundaries that we have from our individual disciplines of engineering to really come forward with this tight-knit solution to meet this ultimate 1.8 kilogram limit. And we are very happy it weighed in just a hair under 1.8 kilogram. So since then, the Mars helicopter Ingenuity has been tested in Mars-like environments, and we have flown it in Mars-like atmospheric density here at JPL, the Space Simulator Chamber. And so with the tests, all tests possible done at Mars, the next thing to do is to test the Mars Ingenuity in the real environment that is being designed and done testing for on Earth. The next destination, launch in space and at Mars. So at this very moment, helicopter Ingenuity is accommodated on Perseverance rover, waiting for launch. And if we could play the video, please. After Perseverance rover lands and deploys the helicopter to the surface of Mars, we have 30 Martian days planned to perform our flight experiments. These will be the very first rotorcraft test flight on another planet. So very exciting days ahead for our team. And in fact, this is truly the high-risk, high-reward phase of our project. We've tested everything we can on Earth, and from launch forward, every event we have will be the very first remotely operated activities in space, during cruise, and all the way to the surface. And so that's very high risk, but very high reward, because all our mathematical algorithms, the tests that we have done, and the actual hands-on experience and learning from operating this very first aerial vehicle in space, they will feed directly into future generations of rotorcrafts of much more sophisticated series, as Jim and Jeff described. Just as the little Sojourner rover was a tech demo that showed how a rover could work, and followed by generations of much more sophisticated generations of rovers. This Mars helicopter Ingenuity could lead to the opening up a whole new way to explore space exploration missions through the aerial dimension. So we're very excited about it, and thank you for having our team. I'm glad to be here to represent our team, and I'm very glad to be here, Tammy. Back to you.
Thank you, Mimi. You can be sure that we've all got our fingers crossed that Ingenuity is going to fly. What an amazing experiment. And so now we're going to fly across the states from JPL to Cambridge, Massachusetts, where Michael Hecht is going to explain what the MOXIE is, what it does, and why it's so important. Hello, Michael.
Hello, Tammy. Thank you very much. Thanks all of you who are listening, and a shout out to the media in particular. We couldn't do this without you. Somewhere out there, I'm at home, obviously. Many of you are at home. And somewhere out there, maybe among the younger folks, there's someone who will someday go to Mars, okay? 15, 20, 25 years, it's going to happen. And when you go, think about it. You'll need things. You'll need a place to live. You'll need a way to breathe. You'll need a way to get around. And you'll need a way to get home. And the first leg of getting home is getting on a rocket and being lifted from the ground to orbit. So all those things, it turns out the single heaviest thing you'll need is a great big tank of liquid oxygen so that the rocket can breathe. Not so you can breathe. You need to breathe, but you don't breathe very much compared to a rocket. Okay, a rocket breathes a lot. And what do I mean by that? Anything that burns fuel breathes, whether it's you, a fire, if you shut off the air, the fire goes out, a jet plane or a rocket. But when you go to space or to Mars, you need to bring that oxygen, and it weighs way, way more than the fuel it's burning. So wouldn't it be great if we could make that oxygen on Mars instead of having to bring it all the way with us? So let me get the model here. This is MOXIE. Okay, this is a solid model, 3D model of MOXIE. And this indeed does what I just described. It makes oxygen on Mars out of resources it finds there. Well, what resources am I talking about? Now, Mimi already mentioned how thin the air is at Mars. There's not a lot of it, but what's there is almost entirely CO2. So can we turn CO2 into oxygen? Well, trees do it every day, okay? We wouldn't be able to breathe if it wasn't for the flora and fauna of this planet that turn CO2 into oxygen. So we want to bring a little tree to Mars as a demonstration. This is, in fact, a little tree. It puts out about as much oxygen from CO2 as a small tree does. How does it do it? Okay. First thing you have to do is collect all of that thin air and compress it. We have, of course, a compressor. This was developed by a company in Colorado, Air Squared, to work particularly on Mars in that special thin air, harsh environment. Once it's collected, it feeds it to this red device. This is called the Solid Oxide Electrolysis System, or a SOX. Being from Boston, I insisted on a red SOX for the model. And that's where the magic happens. So why is it we even know how to build this, how to build something that will turn CO2 into oxygen? We don't often need to make oxygen on Earth. We have all we need. Well, it's because the process that goes the other way is called a fuel cell. When you start with a fuel and oxygen and turn it into a stable gas and get out electricity, we call it a fuel cell. In this case, we're going to go the other way. So what way are we going? Well, we start with CO2, which is carbon dioxide. Obviously, carbon dioxide has oxygen in it. What we want to do is borrow one of those oxygen atoms from the CO2. Why just one? Well, because that way what comes out is CO, a gas, and oxygen, a gas, and gases are easy. You breathe them in, they go out, you have no mess to clean up. So what comes out of MOXIE in this case, or out of the SOXIE, is CO2 that's unused and mixed with CO that is used, and then a stream of totally pure oxygen. That goes into a sensor system which measures it and tells us what's going on back on Earth. And that's basically how it works. I'd be happy to answer more technical questions in the discussion later. Thank you very much.
Thank you, Michael. Moxie, what an incredible little machine, the little engine machine. I tell you, oxygen. Yes. Well, now we're going to go from Cambridge, Massachusetts, down to Johnson Space Center in Houston, Texas, for Amy Ross, our planetary spacesuit engineer. Hello, Amy.
Hi, Tammy. Yeah, I was so excited when Mark Fries and Trevor Graff, the project lead for the Sherlock instrument calibration target, approached me and offered us the opportunity to put spacesuit materials on the calibration target. I'll tell you why. As a planetary spacesuit engineer, I have two primary jobs. The first is to keep the astronauts alive. The second is to give them a good tool to do the work they need to do in. And then the Mars missions that will eventually send humans on are going to be more challenging than any we've tried before. Humans will be on the surface up to 500 days, and they will be doing routine EVAs throughout that time. And so when I send somebody to Mars in my spacesuit, I want to make sure that they stay alive that whole time. I need a durable, reliable spacesuit. To do that, I need to understand how my materials of the spacesuit hold up over that duration of use. So if we can show my first slide. You can see the Perseverance rover up in the upper right-hand corner, and then the calibration target is located on the Sherlock instrument, and the calibration target is shown on the lower right. And so there are round circles above, and then the colors with the round circle and then the squares below it are my spacesuit materials. A calibration target is basically how you can check your focus on a camera, as an example. It gives you a chance to make sure that your instrument is still working properly. And so in addition to those test articles, we have my spacesuit materials. These spacesuit materials are key to the spacesuit's function. Polycarbonate, Vectran, orthofabric, Teflon, and then we're doing an experimental fabric that's one that we haven't used before called a coated Teflon. So if you can come back and look at the materials here, I have examples of those with me. This is a spacesuit helmet. This material here is polycarbonate. On the spacesuit glove, the material on the palm is Vectran. Then the orthofabric is a material that's the white that you see on most of the rest of the outside of the suit. And then the Teflon is the gauntlet and the back of the hand of the glove. And then we have a coated Teflon that's going to be a dust mitigating material. We want to do tests in the Mars atmosphere so we can understand how our materials hold up or don't in that environment. And then we're doing tests on the ground that give us data to compare to that on Mars data so that we can have confidence when we design a spacesuit that we are designing the spacesuit to last for the entire duration of the missions and keep our astronauts alive. This is something my mentor and I had talked about for years. He tried to do it and had to retire after 50 years of spacesuit experience without getting this done. So this is a major career goal for me to have what I think is, to the best of my knowledge, is the first human space flight hardware to go to Mars. And then that feeds my next career goal, which is sending a spacesuit to Mars so our future astronauts can use it there. So I'm really glad to be here too. I'm super excited to be included in the Perseverance mission, and I want to thank my colleague Christine Davis, who did most of the work to get this realized and on the vehicle.
Thank you, Amy. Extraordinary technology with those fabrics. I can't wait to see how they do on Mars. And sitting next to Amy in the studio at Johnson Space Center, we're joined by Michelle Rucker. She oversees a cross-agency team looking at architecture and operational concepts for the first human mission to Mars. So, Michelle, tell us about what the future is going to look like.
Thanks, Tammy. So we know more about Mars today than we knew about the moon when Apollo 11 touched down. And the reason we know so much about Mars is thanks to all of the robotic science missions that Jim mentioned earlier. Those robotic missions have done important science on Mars. They've taught us about the environment on Mars, and that is helping us to design the equipment that the humans will need to be able to live and work on Mars someday. The science is very important for helping us to design our systems, but the technology demonstration opportunities that these missions give us is also important. So Jeff and Michael have talked about some of the technology Those technologies will help us make the missions that we're going to send humans on much safer. So for example, MOXIE, that offers the promise that we'll never run out of oxygen on Mars. I know all eyes are on Mars this month. This happens to be a big month with 3 missions, international missions going to Mars. But don't forget, we're also going back to the moon. Some of the technologies that will be demonstrated on Perseverance will also have applicability to the moon. So the terrain relative navigation system that Jeff talked about, that could just as easily make landings on the moon safer than they were back in the Apollo days. As an engineer, I have to admit, I've been smitten with the Mars helicopter ever since I first saw test footage of it about 2 years ago. My colleagues and I have been like kids in a candy store trying to think of the different ways we could use that technology for a human Mars mission. And I think we have an image we can show. The artists have been going a little bit crazy. It's hard to see there, but this is just an artist's depiction of what it might look like having a human mission on Mars. You see a couple of astronauts there. They've got a pressurized rover in the background. That helicopter, we have just all kinds of ideas for how to use that for a human Mars mission. I know poor Mimi's trying to get ready for a launch, and I've been pestering her with questions. For example, can we use that helicopter as an aerial communications relay in case an astronaut loses line of sight communication back to their rover? Say they go behind a hill or something and they lose their communications. Could we use that helicopter to get an aerial view of the first human lander? Our landers, as Jeff mentioned, will be perhaps 20 times bigger than the robotic landers. We expect those big, powerful descent engines to kick up a lot of dust during landing. If you had a camera up on a helicopter with an aerial point of view, you might get a much better image of the first human Mars mission landing. So we're super excited and I apologize to Mimi for pestering you with questions. Those questions can wait till next week. The human missions will have their day. Today, though, is about the robotic science missions and the technology demonstrations. For my colleagues at JPL, just know that those of us on the human exploration side of the family will all be getting up early next Thursday. We'll be cheering you on as you help lay the groundwork for us to follow. And we're just happy to be along for the ride. Thank you.
Thank you, Michelle. It sounds amazing. We're all going to be cheering Thursday morning. But in the meantime, we do have some media joining us, and we do have a question from Leo Enright from Irish Television. Please go ahead, Leo. Do we have Leo?
Hello?
Hello? We're not able to hear Leo right at the moment, but we also do have some social media questions that we have received today, and so let's throw one out there. From Michelle Johnson, from Darla Jackson, from Facebook.
Hello.
Will Perseverance start building a base camp for future explorers?
That is a great question. So Perseverance is a pretty big robot, but it's not quite big enough to be building the base camp. Perseverance is one of several robotic missions that we've got on the horizon now. We think of these missions, these robotic missions, as more like scouts. They sort of help us learn about the new environment, figure out if that's where we would like to build a base camp. So yeah, Perseverance they won't be building the base camp for us, but it might be very instrumental in helping us decide if we want to build a base camp, whether this is an area that we might want to consider.
All right, let's try our media question again. Leo Enright of Irish Television, can you hear us, sir?
Yes, I hope you're hearing me this time.
Yes, sir, we can. Please go ahead.
I have a helicopter question. I was wondering, what's the experience like going to be for us back here on Earth in that first Wright brothers moment? Are we going to see this helicopter taking off with cameras from the main rover? Are we going to have a live commentary, or is this going to be a much more low-key event?
Mimi?
All right, I'll take that. All right, Tim. Well, thank you for the question, Leo. It's a good question. The operation of the helicopter, it is done remotely, right? So the long answer here, we send up the commands, prepare them a few days ahead of time, send them up, and then the helicopter operates autonomously, right? At a given time, it'll take off, fly, take a few images, come back and land, okay? And then we will have some images that we send back the first day after the flight and landing, and then over the next 2 days, we'll be sending more data related to the flight. So that's the data from the helicopter. And they'll be primarily how did the helicopter perform, what were the onboard voltages, currents, and what were the vehicle state as it was flying, how well did it follow the trajectory. And also we have, as icing on the cake, a few pictures, color pictures that we will take. Again, that's for additional function. So from the helicopter-centric, we'll start getting data back a few hours afterwards on the first day, and then the next 2 days we'll be getting streams of data. On the Perseverance rover side, knowing that where we have commanded the helicopter to fly, the waypoints that we've given, Perseverance rover will be pointing their cameras also along the path trajectory to take images, and will be sending data back. So it won't be instantaneously within minutes, but within the same day, we'll start to see both visual and I'm very biased towards the engineering data, the engineering telemetry on how well the flight went. And then over the next couple of days, we'll get more and more information.
Thank you, Mimi. You're allowed to be biased. The Ingenuity experiment is extraordinary. So our next media question is Jake Robbins, and he must have been preparing for this day because he's calling from We Martians podcast. Go ahead, Jake.
Hi, thank you. Yeah, this question's for Michael about the MOXIE instrument. Assuming everything goes real well with this and it's churning out oxygen like crazy, how scalable is it? Is it as simple as just making one, 100 times the size, or are there new technical challenges that will come after that in making it bigger?
Great question, and I'm really pleased to report that it's a question we're making a lot of progress on. There's a development going on right now in the laboratory testing out these electrolysis systems, the SOx system that produces 100 times more oxygen than what our little one does. And there's a separate project going on developing a full-size compressor. It scales extremely well. And that said, that does not mean the full-scale system is 100 times heavier or 100 times bigger. We expect a full-scale system that can produce 2 to 3 kilograms an hour to be about a cubic meter and to weigh about a metric ton, about 1,000 kilograms. Of course, we will learn a lot from this mission that may cause us to redesign. We have to remember that the full-scale system will not only have to put out more oxygen, but do it for a solid year. So that implies changes in things like dust filtering technology. So it's well underway. It's basically retaining the same design principles and methods.
Thank you, Michael. Our next media question comes from Hanneke Wietering of ACE Media. Hanneke, can you hear us?
Hi, this is Hanneke.
Please go ahead.
The question is for Mimi and perhaps anyone else who would like to answer it. Mars, and in what ways can rotorcraft be useful for future?
Okay.
Mimi, did you hear that?
I didn't hear the whole question. What's the question? In what ways will helicopters be used in the future? Was that the question?
Both for human missions in addition to the robotic missions.
Sorry, Tammy, can you translate? Most of the question
Hanneke,
is
will you
cutting
please
out.
repeat the question, please?
in what ways can rotorcraft be useful for future?
I'm sorry, Haneka, we're having trouble hearing you. Maybe we'll try to get you back on a better line. In the meantime, let's go to some more social media questions. This is for Jeff. Is NASA preparing 3D printers that will utilize Martian soil or material so that we can build storage and living quarters in the foreseeable future? Do we have any plans, Jeff, to go building?
We do, actually. Space Technology Mission Directorate and others have been investing in 3D printing technology. We've actually flown devices to the space station so we can test it out in microgravity. We've been able to produce small implements with those devices on the ISS. We started out printing with plastics, progressed to metals. A lot of liquid rocket engine parts are being printed with additive manufacturing these days, or 3D printers. And we do actually have projects in place that have been looking at using regolith, or the soil that you find on planetary bodies. It's typically called regolith on the moon, to as a binder, or as a component with a binding, some system to bind it together of structures. And so we've been working with Caterpillar and other terrestrial organizations on developing these sorts of technologies with the goal of being able to implement them to build habitats or to build shelters, those types of structures on the moon and ultimately maybe on Mars. So yes, we do have that kind of technology development underway. These kind of projects tend to develop over a long period of time. I was thinking earlier about the new technologies that we discussed for this mission, and we call them new technologies because they're new, being implemented on a flight system and actually flying to another planet. But some of those technologies took 15 years of development to mature to the point and to get an opportunity to be included on a mission so that we can demonstrate them. So it's a long pipeline sometimes where you do technology development and then eventually out the other end comes a technology you can use on a mission. But we have 3D printing technology for planetary bodies in that pipeline.
Thank you, Jeff. I know we have a lot of tiny home folks in America who probably would love the opportunity to go to Mars and build some tiny homes.
Well, actually, one of the organizations we partnered with is Army Corps of Engineers, and they have an interest in building structures in forward operating areas out of materials that they don't have to truck in there.
Right.
And even organizations like FEMA have been looking at it for how could we build something really quick in a disaster area.
Right.
You wouldn't want to live there the rest of your life, but it could be a temporary shelter to get you through a tough period. So there are a lot of ways we could use this technology even on Earth, as we find with a lot of the space technologies we develop.
I was going to say, once again, NASA is leading the way in many technologies that benefit our society in so many ways that we don't even realize. So thank you. Continuing on with more social media questions, we have one for Amy, our spacesuit engineer at Johnson. Amy, Heidi Univic from Twitter asks, how are humans going to keep warm on Mars?
Well, Heidi, I know the most about how we're going to do that with spacesuits. We have extra layers on the outside of the spacesuit that basically protect it from the environment that they are exposed to. And so because Mars has seasons, very much like Earth does, we think that we may need like a winter coat, so you may need insulation that gives you a little more protection. We're going to think about using materials like flexible aerogels to help us do that because of the slight environment atmosphere on Mars. We can't use what we use today in the spacesuits for microgravity, so it has to be different. Also, when you're in your habitat, you need to be able to trust your life support systems. And one of the things that the International Space Station has been able to do for us is really help us explore and develop new, regenerable, and durable life support systems that can also control your habitable volume, your cabin, your house, so that it's comfortable, just like we have air conditioning and heaters here on Earth. So we're getting benefits from the International Space Station and also these future lunar missions for both life support and spacesuits to be able to apply to Mars.
All right, Amy, thank you. And we have one for Michelle, your peer sitting next to you, also from Heidi Univik on Twitter. What do we need to know more about to colonize Mars, and how close are we to sending humans?
That's a great question, Heidi. So I don't know if you caught the NASA administrator's blog post last week. He had an event with on social media, and he mentioned that the first human Mars mission would probably be fairly modest. It would probably be maybe a 30-day mission. That's kind of that's the way humans do things, right? When we go to explore some place new, we don't show up and build a city immediately. We like to scout around a little bit, see whether that's a place that we would like to set up some sort of a settlement. We understand the challenges. We think we know what pieces we would need to be able to stay on Mars for 30 days or perhaps longer. We think it's technically doable in the 2030s, as early as the 2030s, especially if we're able to use the Artemis program on the moon and test some of our technologies there. We'll be able to practice some of our processes and procedures and make sure that we've gotten everything just exactly right before we send humans to Mars.
Thanks, Michelle. Mike in Cambridge, did you have some thoughts on how humans are going to stay warm on Mars?
I did. Thank you for bringing that back around to me. You know, I'd like to bring the perspective of a Mars scientist to this, because this is really one of those mind-bending questions that force you to escape from your Earth preconceptions and intuitions from being an Earthling. Okay, on Earth we have the idea that if we go somewhere cold, we will be cold. And that's because we live in this thick soup of an atmosphere. You know, to a Martian, we would look like fish swimming around in warm water. Now, if you asked an astronaut, such as my colleague in Moxie, Jeff Hoffman, who did 4 spacewalks in the shuttle days, space is really, really cold. But when you, as an astronaut, as a human being, go into space in a spacesuit, you are really, really warm, and you're sweating, sweating like a pig. So the issue then is to stay cool, not to stay warm, because you're kind of in a thermostat. Now, Mars is not space, but it's not Earth either. So for the most part on Mars, despite the fact the air is cold, you're going to be warm because you're generating heat, and it's hard to shed all that heat in such thin air. So that makes Amy's job even harder, because she's going to have to keep you cool as an astronaut and sometimes keep you warm. Fortunately, one of the pillars of being able to survive on Mars is to have lots and lots of power, to have a big capable power system. And as Amy said, we know how to cool and we know how to heat, and we'll have to do both. Thank you.
Well, Mike, stay with us, because our last question is also for you on Moxie. It's from Amal Sabu. He tweeted at us, in what quantity will Moxie produce oxygen, and how will it be analyzed and confirmed that it is producing oxygen?
Thanks, Amal, for asking that. The actual numbers will be 6 to 10 grams per hour. That's compared to an eventual goal in a full-scale system to do 2 to 3 kilograms an hour. 6 to 10 grams is limited to some extent by how thin the air is up in Jezero where we're landing. It's like we're landing on top of Everest. Humans are likely to land in a much lower altitude where the air is thicker, and there we can make maybe 20 grams with the same system every hour. And that's enough for you to live if you don't run around too much. So that's what Moxie will make. And again, it will make it for about an hour or 2 at a time. It'll do this maybe 10 or so times through the first year. So hope that answers your question.
Thank you. Jim, I'd like to come back to you at headquarters. You've heard some of the questions this afternoon. What thoughts do you have? How far along do you think we are into colonizing Mars and sending folks there? It's what everyone wants to know. Do you have any thoughts for us?
Sure. So, having shepherded along these robotic missions, I have a sense of just how difficult it is for the robots to do their job and how many people it takes back at the control centers to guide the robots in their tasks. So I think we still have a lot to learn to develop these systems that not only can support a human and take care of a safe environment for them to live and to take care of all their many needs for survival, but also to move them around. I think it was mentioned that the human systems scale in size by perhaps a factor of 20 over the size of the rovers that we've been sending here. So we still have to learn how to master all of the tasks in going back and forth from Earth, as well as doing work safely on the surface of Mars before we can send humans. And that's one of the exciting things about where we are in the robotic program right now as we move ahead with Perseverance and we collect the, let's call them the souvenirs that we want to bring home, the samples, and then we, through the sample return campaign, we figure out and learn how to bring samples home back to Earth. We'll have solved a lot of the same system engineering problems that the human crew designers have to solve for the larger systems there. But then we have to add the complexity of all of the additional life support and other equipment that we have to bring with the humans. That's being worked on through the human program and the Artemis program going back to the moon, trying to get those systems down so that everything that it takes to support the crew. And on the robotic side, we're trying to get the understanding of the planet and act as precursors, if you will, to figure out the next set of problems that will have to be addressed by the human system. So, we're looking and hoping that, sometime in the 2030s, we'll be able to attempt a first trip there. We'll bring all the system engineering together that we've done in the robotics program and all the lessons that we'll have learned with our return to the moon and put it together. So it looks like it's going to be a very bright and exciting next couple of decades.
Thank you, Jim. You did a beautiful job weaving everything back together again as a bookend to our briefing. This hour has flown by. We are so grateful to the media, the ones that we could understand your questions. I'm sorry that we had technical problems at one point. And we're also very grateful for the social media questions. Again, we encourage you to follow the mission at NASA Persevere. And we would love to keep engaging with all of you. So please keep using hashtag #CountdownToMars and keep sending us your questions and your comments. Oh, here we go. Mars 2020. Thursday morning, our live launch coverage starts at 7 a.m. We will see you back here. And we have a launch at 7:50 if everything goes to plan. And we appreciate you joining us this afternoon. Thank you so much. Go NASA. Go Mars 2020. Good night, everyone.